Hi, welcome to the Points of Topology 6 live session. Before starting, let me know, am I audible and is the screen visible to you properly or not? Please let me know, am I audible and whether the screen is visible to you or not. Anybody please let me know whether am I audible and the screen is visible to you or not. Can you please confirm whether my screen is mm, working fine or not? Anybody please? Okay, thanks, Shumez. And whether am I visible or not? Or is my sound clear? Okay, okay. Thanks, Sumesh, for confirming. So now okay. So now let's start with the problem solving sessions. Okay. Before starting, do let me know that do you have any question or any concerns from the previous live session on the last live session? Do you have any question or concerns from the last live session? Please let me know. Okay, it seems there is no question. Nothing. So let's start by today's session. Okay. So before starting further, uh, 1 minute. Let me check for today's things itself. Okay. So today we shall go with the countability axioms and separation axioms. Okay. 1 minute. Hmm. So first the countability axiom comes to the picture. Okay. So let me write it down for you. Okay. Sorry. 1 minute. Hmm. So today's first topic is the countability axioms. Okay. So, what does the countable axiom tells that? So, suppose, so let X be a space, okay, and suppose X belongs to X, okay, then the space X is said to have countable bases at X if there exists a countable collection beta of neighborhoods of X such that each neighborhood of X contains at least one element of beta. And secondly, a space that has a countable basis at each of its points is said to satisfy the first countability axiom. Okay, or the first countable space, or first countable space. Okay, so what is the full statement? One, the full statement kindly hold a moment, please. Okay, so let X be a space and X belongs to X. So the statement goes as follows. Suppose we have a topological space, okay, and so for first, if first countable, so when a space is said to be first countable, the space is said to be first countable if around each point of X, it is possible to get a first countable basis at each point of X. Now, what does it mean? A first countable basis? That is, there is a countable collection beta of neighborhoods of X such that each neighborhood of X contains at least one element of beta. And a space that has countable bases at each of its point is said to be satisfy the first countability axioms. Okay, so this is the argument. So this means what? So basically, it's the first countable if around each point it is possible to get countable collection of neighborhoods of x. So for example, mm, for example, hmm, for example, if we consider x equal to r, then R, this space R, is the first countable space. Why? Why? Because if we consider the real line, okay, and suppose we are considering any x belongs to R, then we are considering the neighborhoods x minus 1 by n to x plus 1 by x. This neighborhood is x minus 1 by n to x plus 1 by n. This neighborhood, this is a countable collection of open sets of R. So that's why the real is first countable. Okay. Similarly, R to the power n is first countable. Okay. So these are the few things. So there are many examples. So anyway, we are not going to bother about the examples. Now, why this countability is important? Okay. So so first let me know that till now, do you have any question or doubt? Till now, do you have any question or doubt? Please let me know. Okay. Thanks so much. So, okay. 1 minute. Let me check everything is working fine or not. Hello. Hello. Okay. Yeah, okay, everything is working. What does this game now? Okay. So now, so why this thing is important? Uh, okay. So we have seen what? We have seen, suppose why this is important. Why important? Why important? Hmm. So suppose let f is a map from x to y. Okay, be continuous. Then we know, then for any sequence xn converges to x, f of xn, this sequence converges to fx, right? We know all this, and it is a quite all-known thing, right? But the question is that it is so. So if continuous implies this continuous, so there is what continuous implies sequential convergence, right? Continuous implies sequential convergence. Okay. Okay. But the question is that when converse is true, that is the question. Okay. So converse is in general not true, but if so, of course, in general not true. But if the space X is first countable, then converse is true. Okay. So that is the thing. If the space X is first countable, then the converse is true. So this is one thing that's why this first one is important. And second thing is that so so thing is that suppose A is a subset of X. Okay. Now if X belongs to A closure, suppose X belongs to then we know there is sequence Xn belongs to A such that X goes to A. So this is one way we can say. But what about converse? What about converse? Okay. So So the converse is that if x is first countable, then if there exists a sequence xn in A such that xn goes to A, this implies x goes to A closure. Okay. So this is the thing. So that's why this type of countable argument is useful. Okay. So this is the argument. Okay. So now, so this is the first countability. What about the second countability? Okay. So second countability goes as follows. Okay, before going further, let me know, do you have any question or doubt? Please go through the content itself. I shall be back after a few minutes. Please let me know, do you have any question or any doubt? Okay. হ্যালো মুস্তাক, দাঁড়াও, শুনতে পাচ্ছ? হ্যাঁ, শুনতে পাচ্ছ? আচ্ছা, বক্তব্য হচ্ছে যে যেহেতু কেউ নেই, তুমি সম্ভব হবে কি তোমার একটু এক দুটো কোশ্চেন জিজ্ঞাসা করো, একটা কোশ্চেন। না, তাতে কোনো সমস্যা নাই, তুমি জাস্ট কোশ্চেনটা করো, আমি উত্তর দিব। হ্যাঁ হ্যাঁ, ঠিক আছে।
Hello, sir.
Yes.
Hello.
Yes.
Sir, can you repeat the previous question?
Okay. So the previous thing is that, so 1 minute. Okay. So till now we have discussed only the first countability axioms. So the last thing was we have discussed is the following. So we know that if A is a subset and A is a subset of X, then and if there is a sequence X and A, then X such that Xn converges to X, then X belongs to A closure, right? Now the question is that when the converse is true. The converse in general are not true, but whenever the space is first countable, then there exists a sequence X in S as the X must take closure. So basically this first countable criteria somehow closer to a metric space. Closer to a metric space. Okay, so that is the thing. So yeah, so that's what the last point. Do you understand?
Yeah, yeah, I understand.
Okay, thank you, Mustafa. Okay, so now we shall move to the second countable axioms. Okay, well, let me just look into one. So in the meantime, you please go through the content itself. Let me choose some few facts. Please hold a moment. Okay. So now, okay. So now we shall start with the second countable space, or the basically the second countable axioms. Okay. So one might think that why the second countable things come into the picture. So first thing is that there are certain extra thing we will get when we put the condition second countability on some given space. Okay. So the thing. Okay. So let's dive into it. Okay. So further definition: a space X is said to be second countable if it has a countable basis for this topology. A space is said to be second countable if it has a countable basis for its topology. Okay. Okay. So first observation is that second countable implies first countable. The first observation is that second countable is first countable. So how to prove that? Okay, so um, Mr. Sayan Kumar, so you have joined late. So today we are discussing regarding the countability axioms and separation axioms. Okay. So right now we are going to the first countable and second countable axiom, and first countable axiom has been done. So now we are discussing the seven countable axiom. Okay. So before proceeding further, Shyam, can you please, sorry, Shyam, can you please let me know, have you studied this countability separation things previously, or this is the first time you're studying? Shyam, can you please let me know whether these things are you studying for the first time or you have already started these things? Shyam, can you please let me know? Hmm. Okay. So now we are going to prove the second count and first count. How to prove that? Okay. So look, first counter means what? We need to choose that it has a counter basis around each of its point, right? And second counter means it has a counter basis for its topology. Now try to figure out how you can from this you are able to show that around each point it is possible to get a countable basis. Okay, please think about it and let me know. I'll stay back for a few minutes. তুমি যাকে ভালোবাসি, বাঁচবে তার তোমার মুখে Okay. So, so look, second countable space means what? Means they are already exist a countable basis, right? We need the first countable. So let x belongs to x, okay? And we are choosing beta x to all those beta belongs to b such that x belongs to b, okay? So of course, this forms a countable basis at x, okay? So these are things which we are trying to prove that second countable is first countable, okay? So now there are some interesting facts. Now we are writing down now shall we're not going to prove those facts, but we are just um, keeping this as a note. Okay. So first thing is that shit. Okay. So the first thing is that subspace of a first countable space is first countable. Okay. Second is that product of first countable space is first countable. Okay. So this is the second thing. So product means arbitrary product also. Okay. Now there is a theorem and a fact. Okay, this goes as follows: let X be a second countable space. Then every open cover has countable subcover. And second, X is separable. That is, there exists a countable subset of X that is dense in X. Okay. So there are two things. So first thing is the second countable space means every open cover has a countable subcover. And this is known as Lindelof. Okay, Lindelofness. And second is it has a countable dense subset. This is called separable. Okay. So these are the two things we understood. Okay. So now, so these are two things we are not going to prove this, but now, um, let's try to solve some exercises. First question: show that R with lower limit topology is first countable but not second. Show that R with lower limit topology is first counter but not second. Okay. Please try to think about. Take your time and let me know when you are done. Okay. I shall be after a few minutes. Okay. So, okay. So now, can anybody please tell me how that lower limit topology is uh, first countable but not second? Anybody?
Yeah, one second. Hello.
Ah, yeah. Tell me.
Yeah, what is the advantage of the second countable over the first countable? Why we use actually second countable?
Okay, so see, so for the first countable space, what are the two advantages? First thing is the first countable space gives the continuity as a sequential criteria. Also, first countability gives the closure of a set as a sequential criteria. So it is somehow this first countability axioms somehow making the space closer to matrices, right? So now in the same route, we are considering second countability space, which is much more nearer to the being metric space, but exactly not metric space, but it is nearer to the metric space. Okay, that is second countability axiom means the possibility of the space of being metrizable is higher than the possibility of the space of being metrizable, which is first countable. Okay, so all these things are basically becomes closure and a closure to the metrizable space. So that is the thing. And same countability space has some extra corollary over the first countable. So that is why we certainly use the same countability space. Okay. And most of the good topological spaces are all same countable space. For example, manifold. Manifold is a second countable space because manifold, some manifold are metrizable, some manifold we can get define a Riemann metric if you know in that case. But the thing is, the manifold local is a metric, but global it might not be. But local it is a metric. So that is the advantage of concept of second countable. So the first one, okay, understand?
Yes, yes.
Okay.
And
So now, okay. So now let me know why lower limit topology first countable but not second. Anybody? Okay. So first, so l- out of lower limit topology, what are the base of the form? Closed open AB. Okay. Now we want to show that it is first countable. So this means what? We choose some open neighborhood X and there is a counter base we need to figure out. Okay. So now we are choosing the basis X, comma X plus 1 by n. That is, we are choosing third bracket X, comma X plus 1 by n. This forms a countable basis at X to RL. So that's why lower limit topology is first countable. Okay. But it is not second countable. Why? So suppose R is lower limit topology is second countable. Okay, suppose we are assuming this is the case. Okay. This means then it has a countable basis by definition for its topology. Okay. So what does this mean? This means what? For x belongs to x, there exists a bx which is an element of B such the subset of x comma x plus 1 minus. This equation implies that infimum of beta x equal to x. Okay. So now this collection of beta x, this is uncountable since infimum of beta x equal to x. So this tells that, so this tells such beta does not exist. Okay. So this tells that R of L is second countable. So that is the argument. Okay. Is not second countable. Is not second countable. Sorry. So this is the full argument. So please take your time and let me know that is it clear to you. So basically what we have done. So basically, in order to show that R with lower limit is second countable, so we choose we choose that x belongs to beta x and this beta x subset of x comma x plus 1 by n. Then this implies that the infimum of beta x equal to x. So this tells that since the infimum that collection is uncountable, so beta x, the bx that collection is also uncountable. So such a countable basis does not exist. So that's why it is not so countable. So that is the argument. Okay, so please take your time. Let me know whether is this argument clear to you or not. Okay, please take your time. I said about 2 minutes. Okay. So, so now, okay, so now it seems that you understand the argument. So now let's move for the next thing, namely, okay. So now let's next move for the few questions. Okay. Now, okay. So one important fact, let me write it down for you. The fact is the following. Fact is that although R is lower limit topology is not Lindelof, is not Sen countable. What is Lindelof? But this is Lindelof. Please try to. It's an home task. Please try to do it by yourself if possible. Please let me know up by the next session. Okay. Hmm. Oh, so this is a quite interesting fact. Please try to solve it yourself. Okay. And now one more. Now there is one question: is that product of product of Lindelof space need not be Lindelof. Product Lindelof, so need not be Lindelof. So for that, we are going to show that we are going to show that RL cross RL. This is not Lindelof. Okay. So please try by yourself. I mean, so this is the hint actually. So it is difficult to engineer to find such a space. And that's why I'm giving the hint. Please try to solve it by yourself. RL cross RL is not in the left. Okay. So for that, what you need to do, you need to find the open cover which does not have a countable subcover. Correct. Please try to attempt by yourself. Okay. Um, uh, please try to solve it yourself, or else I shall explain it to you. Please take your time. Hmm. Now we are going to show that RL cross RL is not Lindelof. Okay. How to do that? So the idea is first we are going to sketch the idea. Okay. Okay. So idea is as follows. So this is RL2, okay? Now here we consider, sorry, now here I consider line L equal to x comma minus x. Okay. So now, first thing is that this line L is closed in RL2. Okay. Now, second observation is that L is closed, so RL2 minus L is open. Correct. Now, mm, okay. Now, around each point of this line L, we are considering the open set like this. These type of sets are open. Okay. So this is we call it UAB. Okay, UM minus A. So this RL2 will be nothing but union of UA minus A, union of RL2 minus L. Now since RL, if RL2, the point is that if RL2 is Lindelof, then this above open cover must have countable subcover, right? So these are the countable subcode. Okay. So suppose if this is countable subcode, so this implies what? This implies this RL2 can be written as union of A1, A2, AN, U of AI, comma minus AI, union RL2 minus L. This implies that line L is nothing but union of A1, A2, AN, U of AI, comma minus AI. So this means what? This line L is covered by discountably many points, correct? But that's not possible. Why? Because why? Because so this is our line, and so these are the open sets. Okay, but these open sets are uncountable. So, but since these open sets intersection of L, this is only one single point. So this tells that this union cannot be countable. It has to be uncountable. So this is the contradiction. Okay, so that is the thing. So this is the contradiction. So this is the so that's why this union is countable, but this is not the case because we choose the uncountable part. So that is a contradiction. So let me repeat it once. So in general, the product Lindelof of micro Lindelof. Okay, 1 minute, please. Okay. So in general, the product Lindelof might not be Lindelof, but here we are considering the lower limit topology square, which is known as surgeonary plane. We're trying to prove that this surgeonary plane is not Lindelof. Okay. So for that, what we have done, uh,
Hello?
So, yeah, Mustaq, please tell me.
Can you repeat it from the beginning?
Yeah, sure. So we want to prove that the product of Lindelof space is not Lindelof. Okay. So in general, it is difficult to find such space. So here is one example for the lower limit topology. Cross itself, that is RL2, which is surgeon-free plane, that is not Lindelof. We are going to prove that. Okay. So in order to prove that, what I need to do, we need to find an open cover which does not admit a countable subcover. Correct. So we are going to choose some special kind of open cover. So for that, first we are considering, okay, first we're considering the line x comma minus x in the on the plane RL square. Okay. Now that line L is closed in RL square and RL square minus L is open. Of course, I mean complement is open. Now, so RL square, this thing can be written as union of U of A comma minus union of RL 2 minus L. Why? Because RL2, if it is Lindelof, then the above map must contain a countable subcover. Okay. So this is a countable subcover. So RL2 is already union of U of AI comma minus AI for finite countable AI, A1, A2, N dot dot dot, union of RL2 minus L. So this tells that the line L is nothing but the union of A1 comma dot dot AN, U of AI comma minus AI. But this open cover U of AI comma minus AI, these open sets intersects the line L only in exactly one point. So that's why so countable amount of union this does cannot cover the whole line L because the line control of course uncountable many points. So this is the contradiction. Do you understand, Mustaq and Shmesh? Do you understand both?
Yes, yes.
Okay, thanks. So now, okay, so now mm, we're going to, so this tells that product universe might not be enough. Okay. So now there are some few more questions. Mm, let f of x to y be continuous. Show that if x is Lindelof or if x has a countable dense subset, then fx satisfies the same condition. So the thing is that suppose if is continuous x to y, if x is Lindelof or x accountable tensor, the fx satisfies the same condition. So this is what you need to prove. So suppose first you assume that x is Lindelof. Now try to show f of x is Lindelof. Okay. Please. So it is very easy, but so please take your time and think about it, and please try to solve it by yourself now. I'll see you back after a few minutes. Okay. So anybody's confirm whether are you able to solve or at least try to attack this problem? Any idea? Any guess? Anything? Any idea how to solve this problem? Any guess? Okay. So let me solve it for you. Hmm. Okay. Okay. So let x is Lindelof. Okay. Suppose x is Lindelof. Okay. So okay. So now we need to sorry. We need to show what? We need to show that fx is Lindelof. Okay. So this is what we need to show. For that, what do we want to do? So for that, so fx is Lindelof. So this means what? We need to show that fx can be so any open cover has a counter subcover. Okay. So let u alpha be an open cover of fx. Okay. So this implies what? So this implies f inverse u alpha is an open cover of x. Correct. So this implies so this implies that this open cover has finite subcover. Correct. Sorry, not finite. It has a countable subcover. So, so let in that case we can write x equal to union of f inverse of u alpha I is equal to 1 to infinity. And these implies fx is a subset of union of u alpha I is equal to 1 to infinity. So this tells what? So this implies that open cover u alpha has countable subcover. So this argument. So basically what we have done the following. Anyway, there is nothing complicated we have done, but as a whole we have done the following. Okay. So f is the map x to y and suppose x is Lindelof. Okay. So we are first assume x is Lindelof. We are now trying to say f of x is Lindelof. Okay. So in order to show the f of x is Lindelof, what we need to show? We need to show that every open cover is countable subcover. Correct. Now let U alpha be an open cover for fx. Then f inverse U alpha is an open cover for x. And this has countable subcover for fx. Okay. And this is what we're trying to prove or trying to figure it out. Correct. Okay. So for that, suppose x is equal to so since so it's a so now if inverse of u alpha is a open cover for x. Okay. Now since as x is Lindelof, so this open cover has a countable subcover. So x is written as union of f inverse u alpha. This can be written as fx is equal to union of u alpha and u alpha subcover. So this tells that. So this tells what? This tells that f of x is Lindelof. So this is the one-side argument. Okay. So this tells that if x is Lindelof, then f of x is Lindelof. Okay. Now try to show that if x is separable, then f of x also separable. Please think about it and let me know. Okay. Okay. So now let's go to the second part of this problem. Second part is now let, oh shit, 1 minute please. Okay. Now second part is let x is um, separable. That is, it has countable dense subset. Now we need to show that fx is also separable. Okay. So let d be countable dense subset of x. Okay. Now f of d closure subset of f of the whole closure, and this thing is nothing but f of x because d closure is equal to x. Okay. So this tells what? This tells that f of d whole closure equal to f of x, and of course f of d is countable as d is. So this tells that fx is separable. So this is the argument 1 minute. Okay. So what we have done? We have not done nothing extra. So d is a countable dense subset of x, and f of x is equal to f of d closure. Okay. So f of d closure equal to f of x, d is and fx is separable. So that is why we can say that this thing holds. Okay. So there is nothing complicated here. Okay. So now we are going to discuss the base facts that regarding memorizability. Okay. So two facts are that we are going to state the facts. We are not going to prove it, but we using this fact we are going to prove the sum space memorizable or not. Okay. Thing is that every memorizable space which is separable is second countable. And secondly, every memorizable space which is length enough is second countable. So you need to prove this too. Okay. So these are the two.
Hello.
Yes, Mustaq.
Can you explain how countability axiom makes a space close to be a matriceable?
Okay. So yeah, so that's what these two statement. So first statement tells that every metric space which is separable is second countable, and second is that every matrix is within the left second countable. So if the space is metrizable already, then um then either separability or linear roughness implies a second countability. Okay, and also later we will see the following statements. Hold a moment. Later we will see the following statements. That is regular space will the following statement normality plus second countable implies metrizable. Okay. So just so only second countability does not gives metrizability, but extra condition normality, to be precise regularity. So this thing gives the along with the second countability gives the metrizability. Okay. So that's why these things makes a space more closer to being metrizable, but not always true, except certain conditions. So yeah. So that is the thing. Okay. Now using this, now try to show that R with lower limit topology is not metrizable. How? So we have already those two statements. Using those two statements, try to show that R with lower limit topology is not metrizable. Take your time, think about it. Okay. So, so we have already seen that lower limit topology is second is Lindelof, but not say incountable. But the first statement of this theorem tells that metrizable space, which is second countable, must be separable in the lab, must be second countable. So that tells that R of L is not metrizable. Okay, so that is the thing. So using this process, we many times we are able to figure out whether some space is metrizable or not. Okay, so we will see the same, see more things like this, more like this thing in the upcoming session next week, tomorrow. So that's all for today. Today, and so if you have any doubt, any questions, please ask in the next lab session, or you can do an email. I shall definitely get back to you as soon as possible. Okay, so let's stop here for today. We shall make the next session. Thank you. I'm leaving the session.